let's introduce the noisy channel model of spelling. The intuition of the noisy channel, when it comes up throughout natural language processing, is that we have some original signal, let's say it's a word, and we imagine that it goes through some channel. And the idea was originally invented for speech, where there, you talk into a tube or we go over some kind of telecommunications line, and the word is distorted. And so what comes out from the original word is some noisy word. And we've represented that here with a weird font. But in the spelling case, we imagine that, oh, somebody mistyped the word. So the channel is the typewriter or the person typing or the keyboard, and at the end, you get a misspelled version of the word. And our goal in the noisy channel model is to take that output of that noisy process, and by modeling how this channel works, we build a model, a probabilistic model of this channel, we can run all possible original words through that channel and see which one looks the most like the noisy word. So the decoder will take a bunch of hypotheses. For each one, run it through the channel. Here's running hypothesis 2 through the channel, run hypothesis 3 through the channel, and we see which word looks the most like this noisy word, and we pick that as the original hypothesis for the word that started out. So let's look at that. First, we'll introduce some probability, and then we'll look at some examples. The noisy channel is a probabilistic model. Our goal, given an observation X of some misspelling, some word we've seen, some surface thing we've seen, some observation X, we'd like to find W, the correct word. And we're going to model that probabilistically by saying we're looking, the best word, the word that we'd like to replace our misspelling with, is that word out of the vocabulary that maximizes a probability. What probability? The probability of the word given the misspelling. So what word, given that we've seen some misspelling, what's the most likely word, most probable, posterior probable word, given that misspelling? And we're going to use Bayes' rule to replace that probability. So the probability of W given X, we're going to replace that with P of X given W, P of W over P of X. And so we can also eliminate the denominator. So whatever word maximizes this equation will also maximize this equation. We're asking, given a misspelling X, what's the most likely word? And since the formula for that probability includes the probability of the word, the misspelling X, we're including that probability in every W that we're considering. So if some W, say W hypothesis 1, has a greater probability than hypothesis 2 by this equation, it'll also have a greater probability by this equation because X is a constant. X is the misspelling that we're trying to decide if W1 or W2 is a better hypothesis for. So that means that the noisy channel model comes down to maximizing the product of two factors, the likelihood and the prior. And we generally call this term the language model. And you've seen language models before. That's the probability of the error, that's the probability of the correct word, W. And this likelihood term, we often call this the channel model, or sometimes the error model. So we've got two factors, the language model and the channel model. And the intuition is that the language model tells us how likely would this word be to be a word, perhaps in this context, perhaps by itself. The channel model says, well, if it was that word, how likely would it be to generate this exact error? So the channel model is sort of modeling that noisy channel that turns the correct word into the misspelling. Now, this noisy channel model for spelling was proposed around 1990 independently at two separate laboratories, and the use of speech recognition models like noisy channel came into natural language processing right around then, mainly, although not exclusively, because of the work at these two labs, at IBM and at AT&T Bell Labs. And so the examples we're going to take for the rest of this example come from these two important early papers by Mays et al. And by Kernighan et al. So let's look at an example. Here's a misspelling, the word ACRESS. So think for yourself for a second what this could mean. First, we're going to start with generating candidates. What are the possible candidate words to replace this word? And we can think of at least a couple of obvious ways to do this. One is we're going to pick words that have similar spelling. So words that have similar spelling might naturally be mistaken for the correct word. And we're going to operationalize similar spelling as having a small edit distance to the error. Or we could pick words with similar pronunciation, and there we're going to pick words with a small edit distance of the pronunciation to the error. And we're going to, for the rest of this example, I'm going to pick the first approach. So we're going to pick words that have similar spelling as our possible candidates. How do I operationalize similar spelling? Well, we've seen edit distance before. And remember, with edit distance, we talked about the distance between two strings, the minimal number of edits that turns one string into another, where we defined an edit as an insertion, a deletion, or a substitution. So any of these three. For spell correction, we're going to want to add a fourth possible edit operation, transposition, because in practice for spelling errors, we often transpose two letters. And that version of edit distance is now called Damerow-Levenshtein edit distance. And it can be computed, again, by various dynamic programming approaches. So let's look at the candidates that are words within edit distance 1 of our misspelling ACRESS. So here's our error, ACRESS, and here's different possible candidates. So here's a candidate, actress. How does actress turn into actress? Well, the T turns into nothing, so T was deleted. So we have a deletion of a T. So a deletion of a T turns actress into actress. Here, the proposed candidate is the word cress, the kind of vegetable. So here, cress, to turn cress into actress, we have to add, insert an A. So here we had a deletion, here we had an insertion. How about caress? Caress is, to turn caress into actress, we turn a CA into the AC. So we have a transposition of CA and AC. The word could have been access. Here we have a substitution. This C turned into an R. Or another substitution, the word could have been a cross and the O turned into an E. Or an S could have been inserted to turn acres into acres, but the S could have been inserted either here or here. So there's two different ways where this source word could have turned into this error form. So we'll put 2 rows down for both of these possible insertion locations, positions. So I've just shown you candidates that are within edit distance of 1. It turns out that 80% of spelling errors are within edit distance of 1. And almost all errors are within edit distance of 2. So most algorithms either consider just edit distance 1 or edit distance 2 possible candidates. In practice, we also want to allow not just insertion and substitution of letters, but also of spaces or hyphens. So for example, if the user types this idea, we'd like to realize that there should be an insertion of a space, or that the original space was in fact deleted to produce this error form. Or here, the original dash in the word in-law was deleted to produce this error form, INLAW. We've seen candidate generation. Now we're ready to talk about how to rank the candidates. And remember, there are 2 factors. We have the language model and the channel model. Now the language model, we can use any of the language modeling algorithms we've already learned. We can use unigrams and bigrams and trigrams. We can use any kind of back-off algorithm we want to use or smoothing algorithm we want to use. In practice, for very, very large scale, web scale correction, we're going to use, as usual for web scale things, we're going to use stupid back-off. But we might want to use smarter algorithms for smaller kinds of tasks. So let's look at an example of a language model. Here I've picked just a very simple unigram. And in this case, we've computed the unigram from the corpus of contemporary English, one of many possible corpora. And here's some counts. Here's counts of the different possible candidates, actress, cress, caress, and so on. Here's their frequency, and normalized by the total number of words, we get a probability. Here's the total number of words. We get normalizing this count by the total count, we get probabilities. So here's probabilities of words assigned by a unigram language model. How about computing the channel model probability? Remember, the channel model is also called the error model or the edit probability. And we're going to take a simplifying assumption made by Kernighan, Church, and Gale in 1990 when they first proposed the use of the noisy channel model. So let's first see how to do that. Let's assume the misspelled word X has a set of letters X1 through XM, and the correct word W has a set of letters, let's call them W1 through WN. Now the probability of the edit, X, given W, is going to be some set of deletions or insertions or substitutions or transpositions, some set of edits. The way that we're going to model that is we're going to create a confusion matrix. And a confusion matrix says for any given letter, pair of letters, how likely is a particular edit to happen. So for example, for the pair of letters XY, we want to know how often XY is typed as X, meaning how often is a Y deleted when there's an X right before it. We're also going to keep a count of, for insertion probabilities, how often was an X typed as XY. So how often is Y inserted after X? So Y deleted after X, Y inserted after X. Or we'll keep a count for substitutions. How often is X typed as Y? So we meant to type X, we typed Y. That's an XY substitution. Or our transposition. How often was XY typed as YX? So these are just counts. We'll keep a matrix of these counts for every X and for every Y. And notice that what we've done implicitly is we've conditioned our insertion and our deletion on the previous character. So whether Y is deleted is conditioned on X. We could have chosen to condition on the next character or the character 5 to the left or some other thing, but we generally condition on the previous character. So here's an example of a confusion matrix for spelling errors. The font is a little small, but just to give you a basic idea, here's, this is a substitution matrix that I took from Kernighan et al. So here's the letter E, and it's very likely in their data 388 times to be substituted with an A. So you meant to type E, you incorrectly typed an A, or you might have typed an I, or you might have typed an O. So vowels are very likely to be mistaken for each other. Or similarly, the letter M very often gets mistyped as an N. So very high probability of M and N being substituted for each other. They're next to each other on the keyboard, they sound alike, lots of reasons for them to be substituted. So here's our set of confusion matrices, and we just compute 4 of them, one for substitution, one for insertion, one for deletion, and one for transposition. Now I've shown you this table comes from Kernighan et al., but you could also generate the table yourself. So for example, Peter Norvig posts on his website a lovely list of errors. So these are errors taken from Wikipedia and other places that he talks about on his website. And from a set of errors like this, so here misspellings of adaptable as adaptable, or immature with only one M, and so on. So various kinds of likely misspellings. And from this list of errors, we can get a list of counts for every possible single edit error of how often it happens. And from that we can build, so we build our little confusion matrix. And then from the confusion matrix, we can generate probabilities. So every time a particular previous letter happens, we look up in our insertion confusion matrix and we say, how often was xi inserted after a particular letter w sub I minus 1, and we divide by the number of times wi minus 1 occurred, and that's going to be the probability of a particular insertion happening in a word. So we can generate our probability of our surface form for each possible single edit error. Again, we're assuming a single edit now. So only one of these happens to generate our candidate. Whichever one it is, we compute our probability by just normalizing the count of the deletion or insertion or substitution or transposition by the appropriate count and generate a probability. So this channel model, for example, for a word like actress, where we generated ACRESS by when we should have typed a C, when we should have typed a CT, we typed a C, so the word had a CT in it, but the error had only a C. So what's the probability of deleting a T following a C? And if we normalize the probabilities in our confusion matrix, here's the likelihood of this word actress being realized as this misspelling actress. It's 0.000117. The language model, so here's the error model or the channel model. And now we can add in the language model. I'll write LM. So we have the channel model. How likely was CT to be errorfully turned into C, so T to be deleted? And how likely is the word actress anyway? And we can just multiply these together. And what we'll do is, because these are very small numbers, we'll just multiply everything by 10 to the 9th to make it readable. So, so this would be 2.7 times 10 to the minus 9th, but we've multiplied everything by 10 to the 9th here. So you can see that the most likely word here is across with this particular channel model and this particular language model. The most likely word is across, but actress is also quite likely, and acres seems a reasonably likelihood, and the word cress, which is just a very rare word, you can see is a very low probability and has an unusual error of inserting an A at the beginning, makes it a very low probability correction. So the noisy channel model likes the word across as the possible replacement. Unfortunately, we can see from the original sentence taken from Kernighan et al.'s paper that the original sentence, across, is the wrong word. The original sentence is a stellar and versatile actress whose combination of sass and glamour. And it should be clear that this word should have been actress. So across is the wrong word. So just using a unigram model, the noisy channel makes a mistake. So let's look at a bigram model. How well could we do with a bigram model? So we computed a very simple bigram model just using add-one smoothing from the corpus of contemporary American English. So now the probability of actress given versatile, just look at these three words. We'll ignore the rest for now. Actress given versatile, that probability is 0.00021. And who's given actress is 0.0010. So we'll compute those. And now let's do the same thing for another candidate, the original candidate that was preferred by the unigram model, the word across. So we'll put across here instead as our hypothesis. And we'll again compute the probability of across given versatile times the probability of who's given across. So here's those probabilities, and you can see that the probability of who's given actress is much higher than the probability of who's given across. Actress who's is just a likely sequence. And sure enough, if we multiply these things out, the probability of versatile actress who's is a much higher probability than the sequence versatile across who's. So much higher probability. So the noisy channel model with the bigram language model correctly picks the correction actress. How are we going to evaluate these noisy channel and other kinds of models? There are lots of good spelling error test sets. Wikipedia has a list of common English misspellings. There's a filtered version of that at ASpell. There's a spelling error corpus at Birkbeck. Let's look at the Wikipedia list. So there's Wikipedia's list of common English misspellings. And I've shown you here on the slide some various other possible lists that you can go look at on your own. So from these lists of misspellings, you would generate a training set to train your channel model, a development set to test out your model, and then a final test set to see how well your model works. So that's the noisy channel model of spelling applied to non-real words.